All right. Let's get down to business. Question before we get started? No one entering questions. Okay. We're very close. Okay. You learned almost everything there is to know about the universe. It's amazing. So we will talk really briefly about how we know where things are. And then we'll talk about the greatest paradox of the last 100 years. We'll talk about some big questions. And for the next week or so, you should be more confused than when you started. You will learn new things and you'll be like, that doesn't feel good. I don't like that. And that's the right response. If you like it, you really like cosmology, we're just not the same type of person. Okay. There's nothing wrong with it. But for me, it doesn't make any sense. Okay. So the first thing we're going to do is we're going to use brightness. And brightness is going to tell us how far away something is, but we can't use it forever. And I'll show you why that is. All right. So for example, if I know how bright a light is, and you can't really tell in this room, because if I stand under these lights, it's not a very good approximation for how far away I am. But you know that if you take a car light, you put it really far away, it'll look really dim. Then you put it right up to your eye, it'll hurt, right? But we intuitively understand this concept. How much does the light expand? Well, it expands into a circle, and that circle gets larger with increasing R. Okay? So I said that the first thing we have to do is we have to use radar. And we did this. We went to the moon. Some of you may not believe that. Okay. Just Kobe. He's not here, so we can't say anything. We're going to turn half the lights on. Okay. So what we did is we put a really cool system on the moon. And then we sit on Earth. We shoot a laser beam at the moon, at this reflector. And then it bounces the light back to us. But we just count it. We just wait. And once we know how long it takes for that light to go and come back, we know about the speed of light. So we know exactly how far away it is. Once you know how far away the moon is, that can tell us how far away the sun is. Why is that? Because we know that at a specific time of the year, the moon and the sun are almost the same size in the sky. Right? So if I can very accurately measure how big the moon is and how far away it is, then I can use those same angles on the sky to figure out how big the sun is. And now I have an AU. Does that make sense or no? Okay, let's draw that out. Let's see if we can understand that one. Oh God, none of the good chocolates here. All right, I'm doing it anyway. Going in. Okay, here's us. Okay. So that's how big the sun is. Okay. Make some angle on the sky. Okay. Sun's farther away. Sun's 1 AU, right? The moon is like here. And it happens to make the same angle. So if I can measure this distance well, and I know this distance, then all of a sudden I've figured out the sun's distance because I have that same angle and I have the distance between them, right? Right? Okay, because of knowledge. So I have this distance, and that gives me this, and it gives me this. Right? Okay, they're all related. They're all related. So as soon as I get that very first one with radar, then I get all of the solar system. Get every distance in the solar system, like that. You just have to, the moon and the sun is all I need. I can use basic units of AU. Right? Think about the interaction between us going around the sun. Okay, now I can weigh the sun, if I know how far away we are. Now I have mass and I have distance. I can get every other planet. Like that? Okay, let's watch this then, for example. We see Jupiter go around the sun. Right? How long does it take? Some amount of time, right? 5 minutes, 10 minutes, how long? At least 5 minutes. Maybe even some would say more. Some would say years, maybe more than 1 year. What? More than 1 Earth year? Yeah, maybe 1 Jupiter year. Okay. So 1 Jupiter year is longer than 1 Earth year. And we know that it has to do with how far away we are. So we said something along the lines of this, there's this Kepler law that has to relate the period and the semi-major axis. So I can watch the period of all the planets. I watch them all go around. Period, right? And that gives you the semi-major axis of each of them. So all I have to do is figure out what the original A is, that original unit is, and I'm done. Okay, so now I know everything in the solar system. How do I find the nearest star? Well, I can't use that, right? Because we're not mutually orbiting something. So I'm screwed that I can't do anything, right? And that's where all the science broke down forever and ever.
Yeah.
No. What do we use?
Right.
Yeah. We have to think our minds back to the Greeks. Greeks didn't believe this was happening. Parallax. What does parallax mean again? Yeah, movement of things in the back. So as I walk around the room, like I want to do, because I can't stand still, you all move in the front a lot more than those in the back, right? And we have this natural moving of the stars as you go from this point to this point and back again. So there's a tiny bit of parallax. You can't see with the naked eye, but you can certainly see with telescopes. So every January we see the star over here, and every July we see it over here. And as that moves back and forth, which things have larger parallax? Stuff that's close or stuff that's far? Close. So I can get all the closest stars this way. If I just wait 6 months. Yeah, well, I mean, comparatively, right? Okay. So now we did it. Now we got all the close stars, right? Okay. You can use some math. I told you that brightness is falling off like a sphere. Okay. So the same amount of photons has to come out of the surface of the sun. You get out to say 10 AU, then those same number of photons are now on a bigger surface area. So it's just pi r squared. Total number of photons, luminosity, divided by the area that it has to subtend. Okay, so it gets bigger and bigger and bigger. I can get a measure of how far away it is. So if I know how bright the star is originally here, and then I measure how bright it looks, I have a distance measurement. Okay. And these are traditionally what we call standard candles. It's just a metric that we're using in order to understand how far away stuff is in the universe. Okay, that's what that word means. Questions about this part? Okay, so what are the standard candles we use? So that would just be the name of a star. Problem with stars are there's a little ambiguity, right? Well, stars are tricky, right? Because what's that? Because they can be big or small, right? So let's say I look at an object. Let's draw a ASTR diagram. Okay, there's your HR diagram. Okay. If I measure some red star, or sorry, some blue star here. Okay. It gives me the luminosity. Is that now I know exactly what it is? No, why not? Yeah, because you can have this star over here off the main sequence. Same luminosity. Right? Okay. So I can use cluster distance. The apparent brightness of a star's cluster on the main sequence tells us the distance. So I have the whole slope. Here's the whole cluster. And here's the Hyades and the Pleiades. You guys know the Pleiades. You know, Pleiades?
Subaru.
Subaru.
Okay.
You never seen that?
Never
Okay.
seen Subarus?
I feel like we,
Yeah, you've never seen.
the Subaru logo is the Pleiades, 7 sisters. They're all the same word, just in different languages. So it's a cluster of stars that all formed at the same time. The Pleiades and the Subaru and 7 sisters, they're very what color? Blue. Okay, so the brightest ones are these ones up here. 1, 2, 3, 4, 5, 6, 7. 7 sisters. Brightest one. You see all these ones? No, our eyes aren't that good. But telescopes can, right? We can pull them out. And notice they'll be on this side here, surface temperature. These are blue.
So why are they red?
Okay, so here we have the Pleiades, and we know that once we get a cluster like this, we can plot them all up, and we know their color, and we know how bright they appear to us. Okay, and we can use that to normalize different brightnesses. So this is the relative apparent brightness, right? So you say a main sequence of this type would be like, let's say you have, here's your Pleiades cluster and here's your Hyades cluster. You can just align that, right? And you know these ones up here, you're not confused by them because they're off the main sequence. That make sense?
Yeah.
So this one's 7.5 times brighter. So which one's closer? You don't know? Anyone? Think this through.
Would it be the Hyades are closer?
Why are the Hyades closer?
So- Yeah. I think the colors throw me off. Why it's just red? There.
What?
Why is the red?
These are just dots.
Yeah. Dark color.
They're just separating the difference between the Pleiades and the Hyades. You want to make them next time? Okay, I'll make them green and pink. That way they don't need anything. Okay. So if it's brighter, it's closer. Okay, so let's say that a bunch of times. Okay, if I'm closer to a light, it's brighter. Okay, so in this particular circumstance, the Hyades are closer than the Pleiades. Okay, and now I've figured out if I can just look at any cluster of stars, I know where they are relative to one another.
Aren't there some clusters that are inherently brighter, so they can be farther and look the same brightness?
What do you mean inherently brighter?
Like they make more light, like at source, and then when they get to us, it looks the same.
So I haven't, I mean, we didn't go into detail about this, but one solar mass star, exactly one solar mass star, at the same point in its life on the main sequence, will give off exactly the same amount of light.
But wouldn't the clusters have to be the same size for the features?
Well, but look, I can plot every individual star.
But like, don't, like, individual, and individual stars in the cluster, like, they let off different types of light.
Yeah, and they're all right there. These are organized by brightness. I have some bright stars, right? Some massive bright stars, and lots of dim stars. The dim stars are your red stars, your yellow stars. The very few blue ones are the ones up here on the left-hand side, right? Those are your brightest. If you look at 5 different groups of stars, they're all going to have blue stars, and you can see which ones of the blue stars are the dimmest. Those will be the farthest one away. Okay, there's the Pleiades. It'd be cool if you could see that with your eye, though. But yeah, so here's your 7 sisters. 1, 2, 3, 4, 6, 7. 7 sisters, brightest stars in the sky. Okay? Accept that or not? No. Okay. What kind of stars are best for measuring large distances? High luminosity stars or low luminosity stars? Let's vote on 3, 2, 1. Okay, I almost have a unanimous answer. You changing your answer? Does anyone want to explain there? Why do we like low luminosity stars? That's a trick. We don't like low luminosity stars. We like high luminosity stars. Why do we like high luminosity stars? You can see them from far away. As you get farther away, distance gets larger, brightness goes down. If you start with a high luminosity, you can see them from farther. Right? It's like the difference between looking at an LED, right? One on front of someone's car and a candle inside of the car itself. Right? I don't know why you have a candle inside. Okay. So talking about types of star, there's a specific star called a variable star. It's undergoing some life choices, and it turns out that they're very luminous. They live on this thing called the instability strip. So they are going back and forth in this region, changing their luminosity over the period of days. Imagine that the sun was suddenly 10 times brighter and then 10 times dim, and then 10 times brighter over the course of days. It'd be pretty wild, right? We wouldn't be doing well. We'd be doing very poorly. And in fact, there's a whole class of stars called Cepheid variable stars. And they are so consistent in this brightening and dimming that we can actually use these as standard candles. So we observe a star, I don't remember what the name of it is, variable star V1 in a nearby galaxy. So I see this star, not in our galaxy, but in a nearby galaxy, and I can see it brightening and dimming and brightening and dimming and brightening and dimming with this periodicity, right? So this period is 31 days, brightness goes up and down, and this tells us how far away it is. Make sense? We'll go back 1 second here. Here's a star. It lives in this strip, back and forth, back and forth, back and forth. Okay. I can draw it back to its original luminosity. Then I can see how much I measured its brightness for. And that tells us. You see that? Okay, so now I get nearby galaxy. Because if I can tell away how far that galaxy is, then I can tell the whole galaxy is that far, right? It's not like a Cepheid variable is just hanging out nowhere. Right? Okay, now we want to go a step further. Let's say I can't tell exactly, maybe I can't see any of these Cepheid variable stars, but I can see the brightest thing in the universe, and that is a supernova. So there are different types of supernova, but we use these as a standard candle. These are white dwarf supernova because they are so bright that you can see them from the edge of the observable universe, basically up to about 10 billion years. Okay. What does that mean? It means when these stars explode, they give off approximately the brightness of the entire galaxy in a few minutes. Right? Just like bang. So they're really good because they happen all across. Think about how many hundreds of millions of stars there are in our galaxy. You have them going off all the time. As long as you are looking at the whole sky, you can observe these happening. Right? Think about that little picture we had of the Hubble Deep Field and how there was, in every single pixel, basically, there was a little galaxy, right? So you're going to get supernova, and you'll be able to determine, based on the shape of the supernova, how far away it is. Now, I say shape because we talked about the brightness of these things. And if they're really bright, then that gives you distance. Each of these supernovas, whether they're white dwarf supernova, core collapse supernova, they have a specific brightness that they burn at. So it's not like every explosion here on Earth, which can vary. Stars, when they explode, they have a very specific relationship between how long they burn for and how bright they were at their source. That makes sense?
Like exactly the same.
Mm-hmm.
Each time?
Yeah. And we know this because it's physics. There's only a certain amount of energy. right? The whole star collapses and then it explodes. So if you watch that happen, you watch a star explode, okay? It will start to explode and the pieces of the debris will move away with a certain speed, okay? In order to get that speed, which is the end, right? So let's look at the, what's the okay, oh, here we go. All right. So this is gonna be brightness. This is gonna be time. Okay. So star is just normal, living its best life, right? And then it explodes. So suddenly it's very bright, right? And if it's moving apart very quickly, if the pieces are moving apart very quickly, it's gonna become dim very quickly too. Like that, right? Versus if it's moving more slowly, it's gonna have a different length. Like that. So the brightness here and how long it takes tells us everything we need to know about how far away it is. If you like that, you can study supernova. It's a whole field of science. Pretty cool to get to simulate exploding stars. Okay.
Same thing over and over again.
What do you mean? We see these all over the place, right? Here's a distant galaxy before a supernova. Here's while it's happening. Right? Look at how bright this one star is. Here's the galaxy. Here's the whole galaxy.
Oh, wow.
And here's one star exploding. Here's the galaxy. Here's one star exploding, brighter than the whole galaxy, but just for a little while. Right? They're very good standard candles. So they're happening all over the place. Beetlejuice, people talk about this. You guys see it on the internet this weekend? Oh, you're not in that part of Twitter. All right. So its brightness got up to 154% of its usual brightness. It's only about 600 light years away. So, well, that's pretty close for a supernova. So if that were to happen here, it'd be really cool, really, really bright. You'd probably be able to see it during the day. It'd be gorgeous. So two things that are happening. One, Betelgeuse is about to go behind the sun for a couple months. We're really hoping that it doesn't explode while it's behind the sun. And also the time scale for it to explode, probably between now and like 5 million years. so let's stay soon, right? So we think of it in these contexts in human terms. Because in fact, we've seen many stars explode. Just here on Earth, right? We talked about the ghost star that we've seen. We talked about what was it, 1005. There was another star. So we see these all the time. And you know, the last major one we saw was 1987A, which you can happen in 1987. So we haven't had one nearby in a long time. So people want Betelgeuse to explode. I personally don't want Betelgeuse to explode because then that would ruin the Orion Nebula. Then you wouldn't have a red one up in the head. Look dumb. Loses symmetry. What? I was gonna have the bear with no eye. Exactly. Very good point. Okay, so that makes sense. So this is our 5th standard candle, and this allows us to build this independent measurement technique with overlap. So we start off over here. This is Earth. Okay, circular, round. Okay, and we use radar to get the measurements in the solar system. This gives us AU. This parallax gives us nearby stars. Okay, and then we have that main sequence fitting, that wonderful picture with different colors. Okay, that gives us stuff in the Milky Way, gets us out to the edge of the Milky Way. And then we need nearby Cepheid stars. So we start with the stuff that's in our Milky Way, Cepheids, and we can overlap them with the main sequence fitting. We make sure that that technique works, and then we can use it for nearby galaxies. So up here, we have to use nearby galaxies, and then we can use white dwarf supernova out here for distant galaxies. Okay. Okay, and then something really weird happens. Very strange. Why not? So if I measure the average brightness and the pulsation period of a variable star, You can also determine the stars A, age, B, mass, C, distance, and D, rotation period. Now when you're ready to vote, vote on 3, 2, 1. Okay. Why don't you turn to someone behind you and see what answer they have? Did this side all get the same answers?
Yeah.
Okay, what do we think? Let's re-vote on 3, 2, 1. And now it's almost unanimous. What do we think? Is it age? No, it's not age. Is it mass? No, it's not. Is it rotation period? No, it's not rotation period. Can you get rotation period of stars? What's that? If you put a dot on it? Rotation? This one? Not usually. Very hard to get rotation. You get it from Zeeman splitting, but it's really hard to do. Quantum mechanical. You can get distance. So I said that the average brightness and the pulsation of a variable star being Cepheids. This is how you get distance with Cepheid stars. You measure their brightness, you measure their rotation period. Or their pulsation period. And they go from bright to dim, to bright to dim, to bright to dim. Okay. Which of the following distance measures is used to measure distance to the furthest galaxies? You just saw this one, so you should know it. Okay. Vote on 3, 2, 1. You just saw this. Weren't really too much eating, huh? Not enough attention paying. All right, so which one is it? Words. Why is it D?
Right.
Right? It's right there.
The graph says so.
This graph said so, because I did it in that order. It's the last one I said. So for this one, goes to 10 billion years, remember? Yeah. Okay, now. I know. I was standing next to you, but I was blaming other people.
Thanks.
Okay, all right. Okay. So there's this puzzle. And usually when we think about puzzles and paradoxes in science, it's just stuff that we don't understand yet. So I'm going to walk you through a little history. Okay. Before Hubble, and this is a human being. And it's a human being named Hubble. I forget the first name. They argued that spiral nebula were galaxies like our Milky Way. And we have to remember at this time, we didn't have very good telescopes. Okay. Whereas other scientists thought, no, these are just stars, similar to our own. Okay. And this, we couldn't tell how far away these things were. Like spiral objects that you could see with a telescope. We didn't know how to measure them, right? So he measured the distance, Hubble, that's him sitting down in this observatory, measured the distance to Andromeda using Cepheid variables. What are the Cepheid variables? Pulsating stars, right? Things that I just asked you a question about. Oh, right, it might be related. Okay, can't delete everything as soon as he says it. Okay, so he goes and he starts measuring. And he finds that they're well outside of the Milky Way. Right? Andromeda is not close to the Milky Way. Okay? But he also found something really weird. So he looked at, this is say the wavelength, the spectrum of a nearby galaxy. And he found these pieces here that normally line up with some features, say oxygen, hydrogen, etc. He noticed that they're all shifted to longer wavelengths. Now we talked about this kind of when we talked about Doppler shifting. So for example, you see in let's say you're at the NASCAR. Sound of the trucks coming towards us is high pitched and then low pitched. Right? Or an ambulance coming towards you is high pitched and low pitched, or a fire truck coming towards you, high pitched and low pitched, right? Same thing is true of stars. Stars are able to move. If they're moving towards you, they'll appear bluer. If they're moving away from you, they'll appear redder. I am currently doing this to you. Right now I'm redshifted, but you just can't really detect it. It's very small. It's very small redshifted. Right? Okay, so he looks at nearby galaxies, and he sees that all of the features are shifted to the red. So what does that mean? They're moving away. So this galaxy as a whole is moving away from us. Okay? And he looks around and he looks in the Hubble Deep Field. He sees, okay, these are some spiral galaxies. Here's an elliptical galaxy. These ones that look dimmer, they also look redder. Anything that looks far away tends to be redder. So he looks and he looks and he looks and he finds that if you put all of the objects as a function of distance, okay, so the closer stuff here is not moving away from us as quickly as the stuff that's far away from us. So this one here is very far away from us, and it's moving away from us fast. Is that weird? We would expect some stuff that is like, maybe far away from us that's coming towards us. That would seem normal. But no, it's like we farted and everyone's running away. Right? Why are they moving from just us? It's a great question. What's happening? So he comes up with this wonderful law. He names it after himself. No, just kidding, he doesn't. He calls it the recession law, and out of respect, we call it the Hubble law. He finds that there's a way to measure the distance. If you just believe that this is true, okay? You say, well, if I measure how much it's shifted, how much the wavelengths are shifted, I know how far away it is. Okay? And that's a very good measure. Look at how tight that is, right? Extremely close to this line. There are no examples on either side that are far away. Okay. So in fact, if I look at this object here, it kind of makes sense. If I begin to look at it in detail, this thing here is very red. Why is it red? What? It's far away, and therefore it's shifted out of the place that it should be whiter, but we're nearby. But it's far away, so it's red shifted. And so as I begin to look here, I see that all of the farthest objects are red shifted. Okay? And this gets us to the edge of the observable universe. This gets us to, yeah.
So by that logic, the brightest ones over, like those two blue stars are the ones that are the closest to us?
Well, stars are in our galaxy, right? We can't see stars, individual stars in other galaxies. So this one here is a star. These are stars in our galaxy, right? So this thing here is not a star in our galaxy. It's an elliptical galaxy. And I know that it's far away because it's very red. Whereas this one here is very white. Must be close. Okay. So because we can't travel to any of these places, we can only use a limited amount of information. How many pieces of light do I get? What color are the pieces of light? That's it. Right? We don't get anything else. Okay. So this gives us Hubble's law, which gets out to the edge of the observable universe. So Hubble's law relates this very unusual phenomenon, which says that you have, if you're going backwards in time, we can start here and imagine that age or time is the distance divided by the velocity. And if I take those ratios, I just get how long they've been moving away. Right? And it leads to something very uncomfortable, which is the idea that the whole universe used to be very close. And somehow spontaneously came out of nothing. And then it's been moving apart for a long time.
Like it's to expect.
Yes, yeah. The universe is expanding. And the question, there's other questions. One of them is, how is the expansion changing? Is the expansion changing? So we know that everything was close, and now they're not close. Okay, so you're saying to yourself, well, what's the center of the universe then? Right? That's the natural question. There is no center. Okay, let's have a look at this. I should have brought a balloon. Okay. If you had a balloon, just like this, and you imagine 2 points on the balloon, as they blow them up, they are moving apart from each other. But the same thing is true of every other part of the balloon, because the space itself is expanding. So the balloon itself is expanding. This is what we call an analogy. Do not think too hard about this, because it won't feel good. Okay. In this example, this thing is expanding into a 3D universe, right? It's a two-dimensional object in a three-dimensional universe. Our universe is a three-dimensional object, which is expanding in every direction, right? The space itself is changing. Does that make sense?
Yes.
Okay, everyone feels very comfortable, right? Okay. Here's another way of seeing it. Here are the dots, right? After a certain amount of time. Here, B looks like its nearby neighbors have moved this much, but the ones that are farther away look like they moved twice as much, right? Versus here, if I'm A, nearby neighbor doesn't move as much as C and D do. C and D look like they moved twice or 3 times as much. And if you notice, we go back to Hubble's law. How does the distance change with recession velocity? What? Yeah, but what's the slope of this line? Is it a square? Is it quadratic? It's linear. So if I'm twice as far away, I move twice as fast. Let's go back to our analogy with the balloon. If I'm twice as far away, I appear to be moving twice as fast. So this is direct evidence for the fact that the universe is expanding. Okay. Does that feel comfortable? No, you like that one? Okay, here's another analogy. So imagine that you have a rubber band. You have all these little paper clips on the rubber band. As I pull apart the rubber band, the space itself is changing, and the distance between them changes. Okay, so it's true for the red rubber band over here that blue is moving away from it, right? The fastest. But it's also true for blue that red is moving away from it fastest. Yeah.
It's like our galaxies, we don't have stars, or just galaxies.
Yeah, galaxies appear to be moving apart from one another. The only galaxy that's not moving apart from us is Andromeda, which is the one that's close enough that it's actually going to collide. But generally speaking, the space in between us is moving. Now, the thing to keep in mind here is that's probably happening here, right? Space is itself expanding in between us, but it's imperceptible. In the same way, when I drop this object here, the Earth comes up to meet it, right? Drop this, this falls, Earth comes up to meet it. But you never see that happen, do you? Right? Okay, so the space is expanding in between us right now, but it takes multiplying it over length scales that are enormous. So it's only a very small increase in the total amount of space. And you have to wait 13 billion years for it to be noticeable, right? So we might see something, 10 billion light years away, moving away from us at a few hundred kilometers per second. Okay, that's not very fast. And it's fast for us, but it's not very fast for a galaxy, right? Okay. Cool? Not cool? Okay. Do I want to ask you these questions or should we just go to the next one? Let's go to the next one. Ready? I don't know why it's taking so long. There we go. All right. Okay, so now the question is why? Why expand? What? Nothing's stopping it. It could, so it did. That's essentially the answer. Okay. So when we talk about cosmology, we talk about trying to understand the mechanisms as to what we see, but there are certain unscientific questions. What's an unscientific question we're about to run into? Why? Yeah, why did this happen? Not how did it happen, but why? That's an unscientific question. What's another one? Three major unscientific questions that you're going to be tempted to ask that you will not get an answer to today. One is, why did this happen? We don't know. It just is. Number two is, what happened before time? Again, can't tell you. What happens after? We know what happens after. That's still in the perceivable universe. We can predict that'll happen.
Are you sure?
Yeah. In fact, we'll talk about the expansion of the universe and how it's changing. The third one is,
What now?
what is the universe expanding into? Not a scientific question. We can only measure the universe. Okay. Hate it, but we're gonna be fine. Everyone's gonna be fine, I promise. So we're here, solar system. We're looking back through the history of the universe. Let's walk through these different parts. What makes up a majority of the mass in an individual spiral galaxy? Is it A, dark matter, B, massive main sequence stars, C, cold gas clouds, or D, a central supermassive black hole? Let me know when you're ready. Let's vote on 3, 2, 1. Oh, okay. It looks like very few people did the reading. Okay, interesting. What's the answer here? Space big. Yeah, space big. Dark matter. So you want dark matter. Anyone else dislike dark matter? Everyone likes dark matter? It's not everyone voted dark matter. In fact, most people did not vote dark matter. Don't know the answer? No. You like dark matter? Raise your hand for dark matter. Oh, now people like dark matter. What about this one here? Supermassive black hole at the center of our galaxy makes up what percent of the total mass? 4%. Small. Okay. What about this one? Cold gas clouds. You like that? All right. He's pro gold class. What about massive main sequence stars? This one here we know is not true because massive main sequence stars are rare. Remember? There's a lot more red stars than blue stars. You remember that? And they die off more quickly. Okay. So in fact, it's up here, it's dark matter, and I'm going to explain why. So today we're going to talk about dark matter, dark energy, and the fate of the universe. And you'll say to yourself, why did you name it these things, Mateo? I didn't name dark matter, I didn't name dark energy. So I take no responsibility. Okay. All right. So. Dark matter. I don't know, but it pulls. That's the definition. Does not interact with light. The reason that you see me right now, we talked about this when we talked about the 4 ways that light can interact with matter. We talked about transmission, we talked about reflection, we talked about scattering, we talked about absorption. Okay. Dark matter doesn't do any of those. So light is going like this. It hits dark matter and just doesn't play the game. Okay? Doesn't interact. They pass by each other unimpeded. There's yeah, through is a kind of weird way to say doesn't interact. Right? What?
Undetected.
So we have not found it.
So, we haven't found it, but we have a definition for it.
Yeah. So we know that it's there because it pulls. So we know that dark matter exists because we see the influence that it has gravitationally. But we don't see it interacting with light. So imagine a clump of gas, a hot clump of gas or a cold clump of gas. Those are going to absorb light in different ways. Let's say I have a star behind it, and I have a clump of gas. If I look through, it's going to have absorption, right? If it's hot and there's no light behind it, it's just hot clump of gas, it's going to have emission lines. So this stuff doesn't either. Doesn't absorb, doesn't scatter. So we don't know what it looks like. But we do see it pull. Now, dark energy is worse. Dark energy is an unknown form of energy, which seems to be causing the expansion of the universe to accelerate, to increase how much space is moving away from one another. Okay. So when you want to talk about the contents of the universe, you think about yourself, right? You think about this table, right? This makes up about 4% of the total mass of the universe. Okay. And the normal matter that's inside stars is only 0.7% in the whole universe. Most of it is in the cold gas. So it's a pretty good gas. Okay. The ratio here, right? Stuff in stars versus not in stars. It's like almost a factor 5. Right? But this makes up very little of the total mass. Almost all the mass is in dark matter. And most of it's in dark energy. Yeah.
So is space like not empty then, it's just full of dark matter and dark energy?
Oh, there we go. So in fact, we can do dark matter simulations. We do dark matter simulations where, let's say you want to simulate the universe and you don't include any of the dark matter or the dark energy. And then you let it go. You let the simulation run. It doesn't work because there's not enough matter holding galaxies together. Galaxies fall apart. And I'll show you this in a few seconds. I don't like it at all. Okay, so we've used planets. We talked about how we could use them to measure the mass of the sun. We go around the sun, we see how long it takes. We use these laws to measure how much mass is interior to us, right? So for circles, I mean, we're basically a circle. We can do this. We can look at how long Jupiter takes to orbit the sun, and we can get the mass of the sun. Okay, so let's say we have something external to the solar system. It's going around the solar system. I can measure all of the mass inside the solar system, right? Now let's say I look at this rotation curve. Stuff that's close, Mercury, go very fast. Okay, Mars, go more slowly. Pluto, go very slow. Okay, and this curve is right up here. V equals square root GM over R. Right? Okay, that's very different than, let's say you have a merry-go-round. I'm spinning on a merry-go-round. The pieces that are on the edge of the merry-go-round. Oh, God. These pieces here, compared to these pieces here, these have to go faster, right? Get around at the same time. These ones don't have to move as fast. So that's the opposite. It's the opposite. These ones are close, fast. This one close, slow. Close, fast. Close, slow. So we can do this with other rotating things that we see. What's an example of a rotating thing we see in space? A galaxy, a spiral galaxy, right? Now we can measure the rotation curves. So who has the largest orbital speed on this object? It's going around in a circle. And that's a merry-go-round. No, this is the merry-go-round, like a real merry-go-round.
B.
B. Right? We just showed that, right? B. Okay. So if I look at the spiral galaxy here, okay, this is my expectation that the speed will decrease as I go away. But instead, the speed goes to a flat amount. So basically, if I only count the stuff that I can see, I would expect the speeds to drop off. But these speeds out here are roughly the same as the ones halfway in, which means that there's more matter out here that I can't see that's pulling on it. Okay, so this is what we expect. Expect it to go down, and it just keeps going up. I don't like it either. I know, it's very annoying. Okay. So that means that there's more mass spread out than in the solar system. There's more, sorry, that should say galaxy. More mass spread out than in the galaxy itself, yeah.
So we still expect that bottom curve, but just measuring the mass we can see, we haven't even hit the peak yet, where it drops off.
It's flattening out. I mean, this is for our galaxy, but we can do this for nearby galaxies and they look like that. They flatten out. We have a harder time doing it in our galaxy because we're in it. That makes sense?
Why does it flatten out?
So it's flattening out because there's matter out here.
Isn't there also matter in there?
There is, yeah.
Okay, great.
So
Good enough.
okay, so here, this stuff would be orbiting, and the farther that it orbits away, the slower it would have to go, right?
Yeah.
But if the majority of the mass is not found in here, and there's just as much mass on this side, then this stuff will be pulling it and keeping it sped up. But we don't see this stuff. Right? So like in here, so zoom in on that piece, it's gonna be flattish. So that's what we're looking at. We're looking at a zoomed in piece in here. Where the velocity is still flat, because the density hasn't changed very much. It's like moving with one solid body rotation. Okay. Okay. So if we look at the mass, oh, I should have gotten rid of that. If we look at the mass of just material, the mass within the sun's orbit is approximately 100 billion solar masses. Okay, but the total mass, if you just look at the radial velocity of the galaxy itself, is closer to 1 trillion solar masses, which is about 900 billion solar masses of material that we cannot see. So this is what we should think of when we think about a galaxy. You have a teeny tiny galaxy of luminous material. And then you have all of this stuff that we just can't see, which we assume is rotating. We don't even fucking know. It's crazy. And then this is 900 times larger than this is. Yeah.
And it's a speed.
Yeah. I mean, we think,
Is it all rotating in the same direction?
that's what we think, yeah. We can't see it.
So then what's making that rotate?
We assume conservation of angular momentum, but it's hard to tell, right? You don't know what the shape is. We can only look at the result of it pulling on the luminous matter. Right, so we see little galaxies that are floating around, or sorry, little halo clusters that are going around us, and we see the velocity of those halo clusters, right? And they're not behaving like they're only attracted to the matter in here. They're behaving like they're attracted to a uniform sphere of dark matter outside of it. Okay. Okay. So let me ask you a question. Let's see if we can use this brand new information about something that we fully don't understand. If the dark matter in the galaxy were magically increased, how would that affect the galaxy? Would it increase the star's orbital speed? B, decrease the star's orbital speed? C, some stars would be forced to leave the galaxy? Or D, the supermassive black hole would have to change size to compensate? Know when you're ready? Vote on 3, 2, 1. Confident? Everyone says increase the star's orbital speed. You like that or not?
Makes no sense.
Yeah. So we go back to this example. Okay. Oops. This is what we expect with no dark matter. You add dark matter, the speeds increase. You add more dark matter, we don't expect it to increase more. Okay, good. Okay. Here's how we measure the orbital velocities. Blue shifts. We can see this in galaxies. Already showed you. Okay, and here's nearby galaxies. That's the distance from the center. Here's a galaxy NGC to a distance of 200,000 light years, still within the orbital curve. So spiral galaxies tend to have orbital velocities that remain constant at large radii, meaning that the luminous amount that we see, that's just a little bit in the center, and that much more of it is in this extended dark matter halo. Okay. So here's how we tell, right? So we have these rotation curves. We have the velocities of galaxies. We can also do temperature of gas. We see gravitational lensing. What I mean by that is when we talked about the fact that galaxies are massive and sometimes they bend light around them. Right? Did we talk about that or no? This picture? So here I have a cluster of galaxies. And this is actually a background galaxy that's being distorted around it. So here's the real galaxy. And the light is bent because of how massive this galaxy cluster is here. And so it looks like I'm seeing multiple versions of that. This is an event called a microlensing event or gravitational lensing event. And I can use how much this was distorted in order to measure how much matter there is in here. And all of these different values agree. These are independent measurements. Rotation curves, redshifting, velocity curves, the temperature we see from the individual molecules in the gas, and the gravitational lensing. All lends itself the same idea that there is a majority of matter that I cannot see in every galaxy. Okay. So we have two options then, and they both suck. Dark matter does exist, and we're observing the effects of gravitational acceleration. Or dark matter doesn't exist, and we just don't understand gravity. Which do you like personally? One or two? One? Everyone loves dark matter, right? So because we've tested gravity a lot, you have to take one. People have tried stuff like modified gravity, where like maybe gravity changes at long distance, but it has a lot of implications that are unexplainable. So once you start messing with gravity, you basically break it. People have found that this is very, very well testable. Okay. So you have two options. Okay, you can either have, and these are the real names. They're either called machos or wimps. Okay. This is the only place that I think they've gotten creative. Okay, so machos is a backgronym, is where you come up with the name first and then you figure out what it should be. So machos are massive, compact halo objects. So actually our new professor, Dr. Wimberly, studies halo objects. All right. So she looks at like what happens to a galaxy when all the stars die. Really hard to see. So she looks at ultra faint galaxies. But she can still see her galaxy. They're just faint. This could be like completely dead. Okay. Dead or failed stars. Like tons of gas that's not interacting with light. But the problem is here, it still would kind of interact with light if it was normal matter, and we don't see it at all. People don't really like machos. People prefer wimps. Okay, nice life lesson. Weakly interacting massive particles. So what does that mean? We think that the particle probably does interact a little bit with light, but not very much. Weakly interacting. And we think that they're massive. Because rather than have a lot of stuff that doesn't weigh a lot, you could just have a little bit of stuff that weighs a lot. Okay? So you'll have some people who are attempting to find this. They're looking for wimps. They're looking for machos too, but machos seems like it might be dead in the water. So how do you find wimps? Well, you set up a detector to look for dark matter, and you look for anomalous things happening. So you measure the stuff that you can measure. If you had a random interaction, say dark matter, randomly interacting with something, then you can measure it. Oh, I found dark matter. We still haven't done that yet. We're doing it for a while, nothing happened. Okay, so we don't know what it is. Okay. Okay. Yeah, so why not machos? Because of lensing. You can see that, you know, in these lensing events, you have before, during, and after. And this measurement is very precise. We use this to exactly measure the mass distribution. So that wouldn't work. So we think it's WIMPs. I know. It's not, doesn't feel good, but that's what it is. Okay. So if you look at this is a version of space that you're maybe not familiar with, but this is like an atlas. This is like you are here. Okay. And these are the galaxies that we're aware of. Every dot here is a galaxy now. We're not thinking about stars anymore. That's too small. Okay.
Why is it just one direction?
Why is it in one direction?
Yeah.
It's distance.
Oh, okay. I was like, dang, we're just looking at one spot.
In some cases, right, you do have some local time differences, so, you know, 8 to 17. These tend to be, you have some like preferences. It's really hard to see, for example, through the disk, much easier to see out of the disk of the galaxy. So we have a much better view that way and that way. Okay, so a better picture of this would be for you. How about collapsed only a few dimensions here? And the point is that if you look, say, north, up out of the galaxy, you'll see clustering. See like clumps? See clumps? Yeah. So galaxies are not uniformly distributed. They're in what's called superclusters. And then where they aren't, there are voids. Very weird, right? And we think this is because very early on, everything is very close. As it expands, this is a simulation, by the way, of dark matter. which I've illuminated for your ability to see. You start with all the dark matter uniformly concentrated. And because it's gravitationally attracted, it starts to collapse in little areas. And you get these places where it's collapsing. That's the places where galaxies form. That's where you get clusters of galaxies. And the places where the dark matter is not, is where you get voids. And so they do these simulations. And when they run these simulations of the entire universe, and they include dark matter, you get the structure of these clusters and voids. If you don't include dark matter, do not get it. Okay, so okay. All right. Oh, come on now. Okay, so this brings us to okay, I already said that. This brings us to this question, right? If I shoot a cannon and I give it just a little bit of energy, it falls right back down again. If I give it the right amount of energy, it goes into orbit. That's D, right? If I give it too much energy, it flies away forever and it never comes back. So one question we have is, does the universe have enough kinetic energy to escape its own gravitational pull? Okay, so this is the one that's going to hurt you. Okay, you have all of the matter, but space is expanded. So which is larger? The gravitational contraction that pulls all of the matter together, or whatever is making space expand? Which is brighter? Which has more energy? Okay. And so you have this idea like this. Okay, on the left-hand side here, you have a version of the universe that expands, gets out to some critical point, slows down the expansion of the universe, and then collapses back. Right? That's kind of beautiful. It's kind of got a nice symmetry to it. I like this one. It's not what we're doing. You have this version here, which is like the critically damped one. Maybe you expand out to exactly the right amount, and then the expansion just stalls, and we just keep expanding at the same rate. We're also not even doing that one. We're doing this dumb one. Okay? This is a version of the universe where the expansion's increasing with time. Okay. So in here, you would have lots of dark matter pulling stuff together. Not enough dark matter would allow the coasting universe. Okay. So the amount of matter is about 25% of what they call the critical density, suggesting that eternal expansion is the fate of the universe, and that it appears to be accelerating. So this is our universe. Okay. Notice that it's in 2D in this picture. That's a poor approximation. That's time, and that's total size of the universe. So this is a 3-dimensional object that's increasing in every direction. So first we expand very quickly. Big bang down here. And it appears as though the space is accelerated in every direction. And it's increasing that acceleration with time. And this is why we have to come up with a weird thing called dark energy that no one understands and we don't like. Because otherwise we can't explain what's happening here. We've mapped all the matter. We know where all the matter is. Even the matter we can't see, we can map it. You add it all up, then we still don't have enough matter to stop the expansion of the universe. Does that hurt anyone, or is everyone okay with that? Okay. All right. So how can you tell the universe is expanding? So I told you about these supernovae. These supernovae let us see out to like 10 billion years, right? And I can start to map them. Okay. So here's real data. Here's supernova data. Okay. This is looking into the past versus the distance. Okay. So we know how far away these are. And look at this line that they're sitting on. Okay. And they're sitting on this accelerating line. If they were going down this way, right? They weren't that far away. Remember how the distance is, right? If they were closer to us, then we could say, well, maybe we're recollapsing. But they're about as far away as they can be. which tells us that the universe itself must be expanding faster. Every year, space expands faster. Here's the different versions. Recollapsing, critical universe, got to a certain size and stayed there. This is expanding, but not expanding any faster or slower. And this is us. Why? I don't know. No one knows. What's it expanding into? You don't get to ask that question. What happened before? It doesn't, no answer. Okay. All right. So what evidence do we have that the universe is expanding?
Stuff moving.
Stuff be moving. What stuff be moving? Galaxies be moving. Okay. Hubble's law. What evidence do we show that the universe is accelerating in its expansion? What's that? The graph that I just made? No. Yeah, that is Hubble's law. Good. Supernova. It's the stuff that we just showed. White dwarf supernova, right? Let's go back. Let's look at that again. See the supernova data? Right? This could fit in any one of these, right? These could be moving away from us at a different rate. But I can see back in time. Because I can see back in time, I can see how close they were. So this is telling me how close space was when it exploded versus what it is right now. Okay. Okay. So let's walk through the beginning of the universe. If I run it back, basically press rewind on the universe, I take all of the matter and I start squishing it together. When I put all the matter close together, I make it hot in the same way that I can make any gas hot, right? Put more of the gas, press it into a certain area, you're going to increase the temperature. So we know that right after the Big Bang, it must have been really hot. And it must have cooled to what it is right now. And if you look at the time here, this is a great number. 10 to the minus 45 seconds since the Big Bang, that was when it was hottest. And 1 second later, yeah, 1 second later, it cooled down a lot. Okay, so let's see if there's any evidence for this. We talked about this wonderful process where photons can spontaneously create matter. Remember that? Okay, so the early universe is full of particles, creating and colliding, and creating and colliding. And electrons and anti-electrons can annihilate and make light, right? So matter and energy, they're just bouncing back and forth together in this hot soup plasma. Okay? And we can see the light that escaped from that soup. Anyone know what that is? Cosmic microwave background. Primordial soup. Okay, so we're gonna stop there and we'll talk to you about cosmic microwave background radiation. Any questions about this before we break, and then we're gonna do like 15 minutes of break and then we'll do lab? Okay, do you fully get it now? What's dark energy?
No, like, undetected.
But what does it do?
Not like.
The repulsive force that does what?
So it's the expansion.
Accelerates the expansion. What's dark matter? That does what? What do we see it do? We don't see it not do something. We see it do something. What does it do that we see?
It makes galaxies sort of.
Makes galaxies swirl faster than they should. Right? Those are the lines of evidence. When you walk into a bar and they're asking you, hey man, heard you were doing really well in Astro and I wanted to know about dark matter. So, well, I don't really know what it is, but I know what it does. Right? I don't really know what dark energy is, but I know what it does. You see the answers? And they say, well, what about like, what did the universe expand into? You say,
Yeah, the wrong version.
not a science question, sorry. Make sense? Make sense? Okay, alright, let's hit those lights and let's give some of these homeworks back. My goodness, I made a mess of these, so I will try to sort them in some way.